So here's another example of a circuit that might look a little complicated when we first see it, but once we break it down step by step, we'll be able to figure it out relatively easily using the rules that we already know. The thing that makes this circuit tricky is the fact that there are two sources. There's a 14-volt source at the top and a 10-volt source at the bottom. A good thing to start when you're looking at a circuit like this, where you're not given any current, is to trace out and label the variables for all of the different currents in your circuit. Let's start with the sources. If we look at the source at the top, and we're using conventional current flow, which is what we're using in this class, we can start by labeling the current that's exiting the positive terminal of the battery, which we can call I1. If we look down at the bottom, we've got our second source. Using conventional current flow again, we'll draw current that's exiting the positive terminal of that battery, which we'll call current 2. Now what's happening is this current is coming to this junction. This current is coming to this junction, and it's unclear what direction the current will be as it goes through that middle branch. If we're not sure, we can always label it as being in one direction. And then for all of our calculations, we can assume it's going in that direction. In the end, if we've guessed wrong, if this is actually not the direction of the current, then I3 will just come out to be a negative number. So as long as we assume one direction and we're consistent with that assumption, we're fine. We can figure it out. Okay, so I'm assuming that I3 is going from left to right. Now what I can do, now that I've assumed the current's going in some direction, I can label the positive and negative terminals of each resistance. So in this case, as the current travels through the battery, it's having a voltage gain. So it's increasing in potential energy. As it goes through resistor 1, there's going to be a voltage drop, so it's going to lose potential energy. As we travel from left to right through the negative to positive terminal of the source, the current, the charges, will gain potential energy, so that's a voltage gain. As they travel through resistor 1, it's going to be a voltage drop. They're going to lose potential energy. And the way we've drawn this particular current, there's going to be a voltage drop as the current goes from left to right. So I'm going to label it like that for now, and we're going to keep an eye on that middle resistor because the signs will come important when we analyze the different parts of the circuit. Now because I'm not given any information about the actual current, I'm going to start analyzing the circuit by using Kirchhoff's voltage law. So I'm going to create two loops. Here's loop 1, which I'll call loop A, and here's loop B. Loop B. So in loop A, this one's a pretty straightforward loop. The voltage gain has to be equal to the sum of all the voltage drops around that loop. So that means that our 14-volt source gain has to be equal to the voltage drop across resistor 1 plus the voltage drop across resistor 2. I also know that V1 is going to be equal to the current going through R1 times the resistance, which is 4 amps. So that's 4 ohms times the current going through I1. And I can say the same thing about voltage drop across resistor 2. The voltage drop is equal to the current going through it, I3, times the resistance, which is 2 ohms. So that's 2 ohms times I3. So I'll simplify this equation just so I have some nice integer values. And I'm going to call this equation 1 because we're going to come back to this in a second. So that's the first relationship I have between I1 and I3. Now I'm going to go to loop B and I'm going to apply the same Kirchhoff voltage law. So loop B says the voltage gain from this source, which is 10 volts, is equal to the voltage drop across resistor 2, so V2. But if we look over here, this isn't a voltage drop anymore when I'm going in this direction because this is my loop B that I've defined. This isn't a voltage drop anymore. That's actually another voltage gain. So I have to be careful about the direction. That means this is going to be a negative sign. It's not a voltage drop, it's a voltage gain. Now I can simplify this equation just like I did above. V2 is equal to the resistance of resistor 2, 6 ohms, times the current going through it, I2. So that's 6 ohms, that's a bracket, times I2. And the same thing with V3. It's equal to the resistance of R3, 2 ohms, times the current going through it. So that's 2 times I3. So now, simplifying this to some nice integers, I've got 6I3, I2, take away 2, I3, and I'm going to call that equation 2. So now I've got two equations, and they relate I1, I2, and I3. And now I need to find one more relationship that I can use to figure out a third relationship between the three currents. So what I'm going to use is I'm going to just pick one of my junctions, and I'm going to apply Kirchhoff's current law. I'm going to call this junction, let's call it Z. Why not? So at node Z, or junction Z, the current going in has to equal the current coming out. The current going in to junction Z is just I3 plus I2. The current going out is I1. So now I've got three equations. I've got three equations and three unknowns. That's all I need to solve this circuit, to solve for the unknown currents. So if I look at my three equations, the rest is just math, it's just substitution. If I look at my three equations, 1 and 2 both involve current 3, I3. So if I can rearrange these two equations so that I've got one of my unknowns in terms of current 3 only, I can substitute them into equation 3 and make an equation with only one variable, I3. So what I'm going to do is I'm going to rearrange equation 1, so that I isolate I1. That will give me 14, take away 2I3 all over 4. I'm going to do the same thing for equation number 2. So for equation number 2, I'm going to rearrange and isolate for I2. I2 equals 10 plus 2I3 all over 6. And so now what I can do is I can sub 1 and 2, those equations, into 3. When I do that, I'll have one equation with only one unknown, which I can then solve. So this gives me I3, I'll go down a little further, I3 plus I2, which is 10 plus 2I3 over 6, equals I1, which is 14, take away 2I3 all over 4. Now I just have to rearrange this equation. So I'm going to multiply by a common multiple of 4 and 6. So I'll multiply left and right by 12 to get rid of some denominators. So this will give me 12 I3 plus 6 goes into 12 two times, so I'll get 20 plus 4 I3. And on this side, 4 goes into 12 three times, so I'll get 3 times 14, which is 42. Take away 6 I3. Now I'm just going to rearrange and solve. So I've got 12 I3 plus 4 I3 plus 6 I3 equals 42. Take away 20. So that will give me I3 is 1 amp. Now I know that, I can figure out I1 and I2 by substituting back into my equations above. So I1 is 14 subtract 2 times 1, oh that's a 1, over 4, and that gives me 3 amps. I2 is 10 plus 2 times 1 over 6, and that gives me 2 amps. So now if we look back at our original circuit, the only thing we don't know are the voltage drops across each of the resistors. So if we do one more section down at the bottom, we can figure out the voltage drop across each resistor. So for resistor 1, the voltage drop is just I1 times R1. The current we just figured out was 3 amps. The resistance was 4 ohms, so that gives us 12 volts. for resistor 2, same deal. V2 equals I2 times R2. V2 is the current through it, which we just figured out was 2 amps. The resistance was 6 ohms, which gives us again 12 volts. And finally, R3. V3 equals I3 times R3. V3 is the current going through it, which we just figured out was 1 amp, times the resistance, which is 2 ohms, which gives us 2 volts. All done.